This is the final section for GPH 301, Intro to Quantitative Geography. And in this final section, we're going to be looking at heat and the risks of mortality and morbidity, specifically at the language and conventions that are used to communicate and understand the chances or likelihood or probability of dying or getting sick from certain kinds of diseases or causes of death and disability. And we're focusing on heat because, of course, that's really relevant to thinking about climate change. So before we get into the actual calculations, I want to go over some basic concepts that are relevant to what we'll be talking about. So when we talk about the chances of death from anything, we start with the frequency of occurrence, how often something happens. So I have here the statistics from the leading causes of death from the Centers for Disease Control, which is the lead federal agency in the U.S. for tracking vital statistics, which are statistics about birth and death and illness. And these are from 2017. And so what we're seeing here are the total numbers of people in the U.S. who died from these various causes. And so you can see that looking at their first few, the top two are heart disease and cancer, collectively claiming almost 1.2 million people in that year. And that's actually pretty typical, or it has been for the last couple of decades. So it's not unusual. It's a lot of people, clearly, but that's what we kind of expect. Lower down the list, we see accidents. Those are mostly from car accidents. And then we see other types of chronic diseases of the respiratory system, as well as brain and heart diseases. And then we see things that are more associated with old age, like Alzheimer's. And then things that are a little less common, but nevertheless claim a lot of lives, like diabetes and the flu. So we look at these and we can begin to understand what's mostly causing death and what the chances are, because these don't tend to change too much from year to year. But it matters which group we're looking at. These statistics are for the whole population, for everybody who might die. But if we break it down by specific age groups, say, for example, we're just looking at people in the age range of 15 to 24, we see a slightly different lineup of the top 10 leading causes of death. If you look closely here in this table, we have not only the name of the cause of the death, but we have the numbers again, so you can see it's organized by the highest numbers. But we also have the percentages. So, for example, for the number one cause of death, accidents for this age group, we see that 42% of all the people who died that year in that age group died from accidents. And so the percentage is certainly one way we can communicate the chances or understanding where these things happen or how they happen. But the rates are also important too, and that's the last column there. And we see that for that same cause of death, that the death rate was 31.1 per 100,000 people. And that convention of communicating death and also illness is a common one in public health and epidemiology. And it's important because one, you're going to encounter it, but two, because it's a convenient way of comparing populations. So it allows you to look at the deaths in two very different populations, for example, or two different places, and say, are more people dying or getting sick from this cause in this place compared to this place, or amongst this population and that population? And that's important because we often want to understand if something unusual is happening, if it requires some kind of intervention, or if it's deviating significantly from the past, which tips us off to say that something's happening, right? And that's actually how these public health agencies work. They're monitoring these numbers constantly to see fluctuations that aren't expected. And that's important because that's how we know what's going on. If we think about the COVID-19 pandemic, this is the earliest indicator were these numbers, right? The agencies and countries all over the world collect this kind of data, and when they start seeing a spike in numbers, that tells them that something is happening, right? What's interesting about this particular age group, if you look closely, is that the top three causes of death are all violent, right? They involve either accidental or intentional injuries, unfortunately. And degenerative diseases, by contrast, are lower down on the list, which is in contrast to what we saw with the general population, right? And the reason for that, there's a few reasons. One is that this group, this age group, is culturally and socially predisposed to be in positions where harm can happen. And that can be because, for example, in the case of accidents, it's primarily car accidents. That's the leading cause of death for people in this age group. But suicide is also a leading cause of death here. And we know that a lot of mental health issues reveal themselves in this time period for people. And it's a stressful time period. And unfortunately, homicide is also very high, and it's also related to social and cultural circumstances, right? So these aren't biological necessarily differences. They're kind of a function of where this particular group of people are in society at that time in their lives. And so when we look at causes of death, that's one of the important things that I want to emphasize here, is that we think about these things as not just being expressions of biological or physiological differences, but that they're tightly tied to social and economic conditions. And we want to think about those, because those are the things we can change, right? We can't do much about biology or physiology other than maybe prescribing a pill or a vaccine. But society and economy are really big players when it comes to health. So when we look at risks, chances, or probability, there's a lot of ways of expressing that. And so here in this slide, we're looking at the chances of death from various causes. And so if you look in the upper left, looking at cars, dying in a car is a leading cause of death for people in the age group 15 to 24. But when we look at airplanes, for example, by contrast, is a very, very low chance of death, right? I mean, you've probably heard this before, that the chances of dying in an airplane are really vanishingly small. So few people die in airplane crashes compared to cars. So we might know this intellectually, but people are obviously very afraid of getting into planes, even though, again, you're always taking your life in your hands when you get in a car, particularly if you're between the age of 15 and 24. But the numbers that we're looking at, like with cars, 1 in 6,700 is a way of expressing that chance or a probability of that happening. And you could convert that into odds, or into a percentage to say what are the chances or the probability of that happening by simply dividing 1 by that number. We know that the risks, right, which risk is also another way of expressing chances, right? And when we use the word risk, we're thinking, the chances or probability of something bad happening. We can see that risk varies by the type of activity you're engaged in, right? So some sports are more dangerous than others, right? Here we see that the smaller the denominator, or the number on the right-hand side, right, the higher the chances, the higher probability is that something could go wrong, right? So we see hang gliding has a very high probability of death, right? So 1 in 560 means that out of 560 people that go to hang glide, one of them might or probably will die. By contrast, skydiving, oddly enough, has a much larger denominator, the 1 out of 101,000, right? So out of a larger population, you get fewer deaths, right? It's probably have to do with the fact that skydiving has a lot more controls in it when it's done. It's more tightly regulated. We can look at a variety of different kinds of activities, and we see this tremendous variation in the chances or probability of something going wrong, right? And part of it has to do with the way those things work, as well as the inherent risks or dangers that are in them, right? But of course, nothing compares to the most dangerous sport of them all. That's base jumping, if you haven't heard of this before. And essentially, it's kind of like parachuting, except you're jumping from a fixed object on the ground, either a building or a cliff or something like that. Although you're usually using a parachute, you're not jumping without a parachute. Nevertheless, because you have such a short period of time to open your chute, the chances of dying are very high. So you can see again in this one, the number on the right is a lower number, meaning that in a very small population of trials of people jumping, at least one of them is going to die, right? So now I could ask too, what is your risk of dying from this kind of activity, right? And the answer might depend on whether or not you do base jumping, right? If you don't base jump, then you have zero chances of dying from base jumping, right? And that sounds silly, but that's actually a key concept. And when we talk about the risks or probability of something, whatever it is, right? Whether it's a disease or some kind of accident, it matters whether or not you're exposed to the risk, right? Whether or not you engage in an activity where that's a possibility, right? If it's not possible, then it can't happen, which seems redundant, but it's worth saying because, again, we kind of express these numbers or these probabilities as if they're kind of universally true, which is not true. They're only true insofar as you could possibly be in the population that would be exposed to them. When we talk about risk too, we often want to compare the risks between people, between groups. So take, for example, smoking, right? We've known for a long time that smoking is dangerous for your health and can lead to various forms of death. We tend to focus on cancer, but as it turns out, actually heart disease or heart attacks are often a common side effect of smoking too. But in any case, we look here and we see that the women, let's start on the right, women, it says, are 12 times more likely to die from lung cancer than non-smoking women. And essentially what that means is if we looked at all the women who died from lung cancer, right, we just said everybody who died from lung cancer who's female, and then we separated out those who smoked and those who didn't smoke, we'd find that the rate of death for those who smoked is a factor of 12 times more than those who did not smoke, right? And that simple comparison is what makes this number possible. That shows, how much more likely. We see here that with men, it's even more dramatic, 22 times, right? So for men, that's a really big difference, right? In terms of the risks of dying from that particular cause of death, right? From this particular type of activity. If you don't smoke, right, then you're not going to be exposed to this problem, right? And your risk will be lower, right? Because in this case, what we're looking at is two populations, but if you don't die from lung cancer, right, then you're not going to consider it into this. This is only looking at people who died from lung cancer, and we know that smoking is a big determinant, but we know that other things can cause lung cancer too. So it's not like this necessarily applies to everybody equally, right? We also know increasingly that not everybody is equally susceptible to developing cancer. Some populations are more susceptible to that. We're interested, though, in looking at the weather. So we're kind of going in a slightly different direction. So we're looking at heat. So far, we've looked at flooding and we've looked at hurricanes, right? Those are the two biggies that we tend to associate with climate change risks to people. And those are, in fact, dangerous. But when we look at weather-related causes of death over time, it turns out that heat is actually the number one cause of weather-related death. Which is astounding, right? Because we always hear in the news about hurricanes or tornadoes, for example, and those are certainly dangerous. But heat is something that's not very spectacular when it happens. It tends to be one of these slow killers, but it happens all the time. And the worry is that it's happening more frequently because of climate change. And it does claim a lot of numbers. And so we want to look more closely at that and learn how to dissect the data and kind of communicate how that risk plays out for the general population, but also for specific groups, because we want to identify who is most at risk from this particular hazard. Now, how does heat kill people? Well, in a variety of ways, as it turns out. Obviously, we've probably all been exposed at some point to uncomfortable heat, but we don't always know why it does it to us, why it's uncomfortable. And it turns out that the body has to work kind of hard to maintain a constant temperature, and this is key to your health, is maintaining that temperature. And when you're exposed to excessive heat, the body has to work much harder to do that. If you already have an existing health condition of some sort that makes it hard for your body to adapt, it could be that much worse. If you get too hot, it's not just a lot of sweating that can happen. You can actually get really, really sick. It can cause people to faint. It can cause people to get strokes, basically blockages in their brain from blood clotting, and these can lead to serious disability or even death. So heat is no joke. It really can be something that can cause significant injury, if not death. And finally, we know that with heat, heat isn't all the same. This graph here is a heat index, and you might have seen this in the weather reports periodically when we've had a bad heat spell, but it highlights the relationship between humidity and the temperature that the thermometer shows. And it turns out that the humidity has a lot to do with how we feel. And on a dry day, the temperature can go fairly high, and although it might be uncomfortable, it has to get pretty high to be dangerous. So we can look along the top row. We can see that we're looking at temperatures where there's a low relative humidity, a lot less water in the air. And so we get into the high hundreds, or let's say higher hundreds, before it becomes dangerous, right? But if we encounter a situation where we have relatively high humidity, the danger zone arrives much earlier. So for example, if the relative humidity gets up to 80% or so, right, looking on the left-hand column, and then we will work across to the temperatures, we can see that at 94 degrees, which is pretty warm, admittedly, but at 94 degrees with 80% humidity, what the index shows us is that it actually feels like 129 degrees to us. And the primary reason is that the body, in order to cool itself, well, we sweat, right? You know that inherently, but sweat works by it cools you rather by evaporating. So when you sweat, the water that's produced on the surface of your skin evaporates, and by virtue of evaporation carries the heat away from your body, right? This is a chemical reaction, or a physical reaction rather. But if it's really humid, it means that the sweat can't evaporate as easily into the air because the air is already saturated with water. And so if your sweat can't evaporate easily off your body, it makes it that much harder for your body to shed that excess heat, right? Because it doesn't go away. And so you sweat even more to try to get rid of it, which sometimes can have the perverse effect of actually making you feel even stickier and making it even harder to cool down. But nevertheless, that's what's going on. And so that's where the threat comes from. So heat is something that's very real in terms of the threat it poses to people. And it works in a relatively straightforward way. But as we're going to find out, it doesn't play out the same for everybody. And that's what we're interested in finding out in this series of exercises. So with that, we'll move on next in the next video to start working on the actual numbers, to start analyzing how we communicate the probability of death and disability from heat.